Hi, I'm Marta Stoeckel. I am a high school science content specialist and a physics teacher just outside of St. Paul, Minnesota. And I'm going to share a strategy that I use to help students make connections between science and engineering using evidence-based reasoning. Before I dive in, I want to make sure and thank Angela Peterson and Lisa Ortman. The strategy I'm going to share comes out of some curriculum that we co-wrote together as part of the engineering team's project. Now, early in my career, when I did engineering design challenges, I tended to find that students didn't necessarily see what the engineering had to do with the science they were learning. And they frequently relied on a lot of tinkering, where they just sort of played around with the materials to figure out a good solution without ever really engaging with the science. And so my driving questions when I try to think about an engineering design unit are: what science are students using in this design challenge, and how am I going to know that students are using that science? Because I find those questions really help me to make sure that that science is going to stay connected to the engineering. When I do some kind of unit built around an engineering design process with the goal of integrated STEM instruction, I tend to use this version of the engineering design process. It's not the only version, and there's definitely some debate over how well any version can really capture what an engineer does. But this is one that I found works pretty well for me. We start the unit with the problem, where I introduce students to whatever that engineering design challenge is going to be. We spend time figuring out what are the criteria and the constraints, things like that. Then we dive into the background. That's where I have students learning the science that they're going to need to address that engineering design challenge. Next, we go into the plan phase, where students take what they've learned and they figure out what are they going to do to try to solve this engineering design challenge. What are some solutions that might work? The implement phase is where students actually put those solutions into practice. And then the test is where they do something to collect data on how well their design actually worked. And in the evaluate phase, they take all that data they gathered during the testing and figure out what worked well in their plan, what didn't. And then something that's not shown in this diagram is that at just about any of these stages, it might make sense to jump back to an earlier stage of the engineering design process, to dig back into some earlier piece before you're really ready for what comes next. And so it's not this truly linear process. In thinking about how to make sure that students are connecting the engineering and the science, I tend to really focus on this plan phase, because in terms of the engineering design process I use, this comes right between the background, where we're really focused on the science learning, and the implement, where we're really focused on actually doing the engineering. So during my plan phase, I make a lot of use of this graphic organizer, which is based on the CER. This structure also fits really well with NGSS science practices of arguing from evidence. We replaced the claim with the idea. So that's where students come up with some kind of idea for a potential solution to the engineering design challenge. The evidence is then their science knowledge, data from labs, things like that support the idea. And the reasoning is putting into words how that evidence supports their idea. You'll notice that this also includes a section for restating the problem, including criteria and constraints. One definition of engineering is design under constraint. And so I think it's really important to make sure that students are keeping the problem and what defines a good solution at the front and center of their thinking. The other section that you don't normally see on a CER are the assumptions and simplifications. Anytime we build an engineering design challenge around some kind of real-world problem, what we actually do in our classroom is some kind of model of that real-world problem and potential solutions. And whenever we make a model of something, we have to simplify and we have to make some assumptions. Stating those explicitly can really help students buy in to the validity and the authenticity of the engineering design challenge. Plus, it fits really well with the NGSS scientific practice of models and modeling, which calls for students to be able to recognize the assumptions and simplifications in a model. So here's an example from one of my students. This was a project where students designed a cargo carrier to protect an egg in a front-end collision. And so under the problem, that student is summarizing what have we defined as a good solution and criteria that that solution needs to make. And then under assumptions and simplifications, we're only going to worry about that front end collision, and we're not going to think about how will we get from whatever students build onto the little piece of 2x4 up to something that could work on an actual truck in the real world. Now the idea here, this student thought to take a Dixie cup, line it with cotton balls, and then shove the egg right in there. I've got no illusions. This student very, very well could have come up with this idea by tinkering. In fact, solutions like this are often students' first instinct. But what I think is useful here is that this student was able to articulate how Newton's second law justifies that this is a good idea. The student was able to recognize that because of the squishiness of the cotton balls, that egg is going to have some extra time to slow down, which means there's going to be a lower acceleration and therefore a lower force on the egg than if it hit something harder. Now, in terms of how I use this in my class, when I'm doing one of these lessons that's the plan phase of the engineering design process, I have the materials available for students to see, but not to use or manipulate. I don't want a kid who doesn't know what I mean by a Dixie cup to be at some kind of disadvantage. There's a lot of variation in what cotton balls look like, and so I want kids to see what are the cotton balls they're going to be able to use. But by only having enough for students to look at and see as samples and not materials for them to work with, that short circuits their instinct to just start tinkering right away. I also start by having students work individually. I give each student a paper copy of this graphic organizer, and I give them some time to fill it out on their own. This means that by the time they get to groups, every single kid has an idea, or not only has an idea, but knows why it's a good idea and what science learning supports that idea. That can help disrupt status by making sure that every kid has something to share, and makes it that much harder for the group to just go with the first kid to speak up or the one that pushes their idea with the most authority, because every single kid knows what's good about what they're thinking. Now, once students have had time to work individually, we move into small groups where I give students whiteboards and have them as a group come to a consensus on a design that they justify using evidence and reasoning. I'll also often have groups pair up so that each group can share their design with another and again practice that justification for their idea. Now, anyone who's used CERs knows that it's really tough to get students to go as deep as you'd like, in particular on that reasoning portion. And so throughout this process, while students are working, I do a lot of circulating, talking to groups, asking lots of questions to push students to think deeper, and often explicitly cueing them. Hey, what you said right there is really good. You should add that to your reasoning, which really helps students start to develop that idea of what counts as good reasoning. Now, in terms of the student response, this is a quote from one of my 9th graders at the end of that cargo carrier project. You can actually understand because you need to know in order to do stuff and be successful with it. And so this student was really seeing how the science that she was learning was important to this engineering design challenge, which was really motivating and really helped her to understand it at a deeper level. So thank you very much for watching. I would love to hear what engineering design challenges you use with your students and how you make sure that your students are connecting science to engineering.